Hello everyone, welcome to our literature presentation of the development of a computation model or a fluid solver for major arterial flow. Our names are Akram and Ahmed, and yeah.
Alright, now onto our project. Our goal is to try and develop a computational model, also called the fluid solver, that just emulates blood flow, how it behaves, and how it moves in major arteries. They're usually made to understand flow physically and to assess said flow for possible disease markers. Alongside learning countless concepts and providing a portfolio for future prospects, this project was made as means of making an educational, research, and possibly to a degree, clinical tool, all to simulate and understand blood flow.
Now, first of all, as we all know, blood is a fluid, but its properties are what we call non-Newtonian, meaning that it doesn't follow Newtonian mechanics and laws. Because of that, we have to consider specific rules to approximate fluid flow using different variables.
And in general, most fluids, such as water, behave typically when you squeeze them. They just move. But non-Newtonian fluids, however, behave a bit differently, as their viscosity actively changes in reaction to the force you apply on them, which is, just for all intents and purposes, called shear stress, this force application. And for example, some have their viscosity decrease when you apply force on them, for example, like ketchup when you squeeze it out of a bottle. This is usually called shear thinning, and others do the actual opposite, and they actually have the viscosity increase as you apply force on them. This is what we call shear thickening. Choosing the right model is important to actually accurately describe this behavior for purposes of any simulation or model or etc.
Now, the main disease that we'll work on, which is by itself is an umbrella term, is called arteriosclerosis. It's a chronic process that begins during childhood and your adolescence years, and it's practically the buildup of lipid-rich plaques. Those plaques are made up of cholesterol crystals, foam cells, smooth muscle tissue that break up from the arterial wall, which may calcify in later stages depending on the region. As those plaques grow, arteries first of all lose elasticity and become narrow, meaning they stiffen and they harden. Flip it. Anyway, leading to a reducing blood flow, of course, leading to many diseases and complications such as you got coronary artery disease in the heart, ischemic cerebrovascular disease, or what you call CVA, cerebrovascular accidents, practically strokes, and peripheral arterial disease in the lower limbs, and a ton of other complications. So to assess those diseases mathematically, we use something called hemodynamic factors. So basically, they govern how blood can and should behave at certain conditions. And if those principles don't act accordingly, well, that means there is a major issue when it comes to the flow. The main ones are, first of all, you got wall shear stress, which is how much force that blood is applying on the vessel wall. Second of all, you got viscosity and laminar flow. So first of all, viscosity, the official term is the internal friction of a fluid, but in simple terms, it would be how sticky a fluid is. So for example, honey is viscous more than water. Then you got laminar flow, which is how smooth a flow is. So if a fluid is laminar, then it is smooth and flowing. But if it's turbulent, that means the opposite, which might indicate different conditions in different regions of the body. Lastly, you got the Hagen equation, which states the relationship between a vessel's radius or blood vessel's radius and pressure. When you decrease a vessel's radius due to, for example, arteriosclerosis, that will equal to an increase in pressure to a factorial of 4F, I believe.
Right, and now come to the computational models, and I hope you're following us so far. They are just equations and systems used to simulate or solve something for a third purpose, and this also extends to fluid models. Choosing the right computational model can allow for more accurate and faster results, with two being, based on our literature review findings, we've chosen these two models. One, the smooth particles hydrodynamics, which is just SPH for short, and the Lattice-Boltzmann method, which is just LBM for short. And as a general note, we want to say that SPH is more accurate, but also heavier computationally, whilst LBM is faster and easier to set up, but can be a little inaccurate and unstable at times. To actually visualize this, just take this for example. The main differences between SPH and LBM is that SPH is a Lagrangian method, which in simple terms is just we're following a dot or a particle tracked over time and space. We're just splitting the entire fluid into a bunch of small particles, like for example in this example video. Whilst LBM here is just an Eulerian method, meaning it has a universal grid that we just refer everything to actually state what should go where, in what direction, how fast, and how much should it rotate, etc., etc. All of these specifics are just essentially governed by this grid.
Now, here's how our solver would look like in sort of like a pseudo image. In simple terms, you would have first of all the vessel geometry. You'd have initial values. So you got the pressure, the flow rate, and the viscosity of the fluid, blood. So therefore, as the fluid moves from the inlet of the vessel through a geometry that would have been imported from, let's say, a CT scan, making it what we call patient specific. It moves out from the vessel all the way out to the outlet. So far, you're gonna know only about the vessel. So to ensure accuracy of the model, we use something called a lump parameter or a Windkessel model. Practically, the Windkessel, in simple terms, it's a way to calculate the cardiovascular system rather than out a geometry like the simulations that you just saw as a geometry in a fluid, but as an electrical circuit. So we got resistance and compliance, peripheral resistance, etc. It's a zero dimensional, so it doesn't need space. Where you would calculate the flow for the rest of the body, so you got the heart, the other major arteries and whatnot, the values would go up back to the inlet again, and then you would use those values as your initials again, over and over and over again, sort of like creating this cardiac cycle. As a final note before we end this, while the solver isn't intended for clinical use, it shows how computational models can support cardiovascular risk assessment and possible future research that is happening as of now among the academic community.
Exactly. And now we can move on to some quick reflections before we finish this presentation. We just want to say that we managed to improve our research and learning skills, tackling all these new concepts of varying complexity and different applications, different contexts. There's also we understood the importance of a diverse and open mindset because it also aided with the previous example. And finally, we just want to say that we better understood our own limitations in all of our understanding and learning, and also knew when to stop and to try to employ more diverse or newer methods. So yes, here's our sources, and yeah, thanks so much for listening.